Let's talk about logarithms. So an exponential function usually comes in the form y equals ab to the t. Usually t is time. I'm just going to say ab to the x. Input variable, output variable. A is your starting point of your exponential function. And b is going to be your multiplier. How much is the exponential function increasing or decreasing? For my example with logarithms, I'm actually going to simplify this a little further. If I start at 1 and make a 1, then 1 times all this stuff doesn't change my b to the x. That just stays the same. So an exponential function can look something like this. It's a very simple, basic exponential function. A logarithmic function is the inverse of the exponential function. Now remember, for inverses, you just swap the x and y and then resolve for your new y. Now, this looks really weird because all of a sudden I have a log here. And the reason why I have a log when I have to solve for y is because in order to get this exponent down from the top, I need to use a logarithm. And just so you can kind of have a visual, the exponential functions look like this, where they have a starting point and then their multiplier says how much they increase, or you could have a decreasing exponential function. And then the inverse of that is the logarithmic function. Okay? And it is reflected over the axis y equals x. Now, how do we get this to this, right? That is what I call the circle of life. I'm going to give you the math way to say it. So we're going to say log with some base. And they usually use a here, which is kind of confusing, but I'm just going to go with what the textbook says. Log base b of a equals x. If and only if and only if b to the x equals a. Okay. So basically what's happening is this thing is getting rewritten to look like this. And there's a rule for that. And I reference this as the circle of life. Okay. Okay, that's better. So this now reads b to the power of x equals a. And that's kind of how it makes this circle, right? It's the circle of life. So anytime you see something written like this, it can actually be rewritten like this. That's where the if and only if statement that I said before can be shortened as like a longer if. So it means it can go both ways, right? So if I have this, I can rewrite it like this. And if I have something in the log version, I can rewrite it in the exponential version. So let's look at a quick example. So like log base 2 of 8. Pause the video. Do you know what that equals? Log base 2 of 8 equals 3. But why? It equals 3 because 2 to the power of 3 gets me back to 8. Boom. All right. How about a square root? Log base 3 of root 3. Pause the video. What do you think that equals? That equals 1/2. And now try pausing again. Can you do the rewrite on this? Because 3 to the power of 1/2 is the same thing as the square root of 3. And maybe you didn't remember this, but doing the rewrite here, you can see, oh, the square root is really just a fractional power. In fact, the fraction of 1/2, right? Cube root would be the fraction of 1/3. Fourth root, 1/4, and so on. How about this one? I feel like this one's not so obvious. But pause the video, do the rewrite, see if you can see it. All right, 5 to the power of -2 should equal 1/25. And I'm just going to show one more step here. Anything to a negative power, we got to move it downstairs, right? So 5 to the power of -2 over 1 is the same thing as 1/5 squared. And now we can see 5 times 5 is 25. There are some basic properties of logarithms. We're just going to set this up like real true mathematician style. I'm going to say for all the values of b, that are greater than 0, fancy way of saying positive, and b is not equal to 1, also where x is greater than 0, and y is an element, of any real number. Y equals any real number. Then property 1 states for log base b, I should use the same capital. Log base b of 1 is just 0. Do the rewrite for that, pause the video. Because b to the power of 0, anything to the power of 0 is 1. Log base b of b b to the power of what gets you back to itself, because anything to the power of 1 equals itself. Log base b of b to some other power equals what? If I rewrite this, b to the power of what gets you to b to the power of y, right? B to the power of y is b to the power of y. And finally, b to the power of log base b of x equals just x. And this one is a little crazy. Oh, it's starting to get hard for you to see. This one is a little crazy to rewrite, but here's the rewrite on it. This is because log base b of x equals log base b of x. So let's do another example. How about log base 2 of 8? What does that equal? Well, 8, I'd really like to rewrite this so that I can see the exponents that are going on here, right? Because I know there's a 2 involved with that. So I could rewrite this as log base 2, and 8 is really 2 cubed. And so now, using our property, right, where we're here, and we have log where the base, and then it's the same thing as the base to some power, what does that equal? That equals just the power. So here, this is like 2 to the power of what? 2 to the power of what gets me back to 2 to the power of 3? Boom, 3. Let's try that square root again. How about log base 2, or let's do base 3 of square root of 3. What does that equal? Well, you're asking the same question. 3 to the power of what gets me back to 3 to the power of 1/2? One half. Now there's two major types of logarithms. One is the common log, and the other one is the natural log. The common logarithm is base 10. And so we always just write log, L-O-G, of stuff. Let's just say of the number 1, right? We don't write the 10 down here for base 10. I'm not really sure why, but it's always a thing where if you have a base different than 10, then you write it like log base 2, right? Of 8, like we looked at before. You could have log base, I don't know, 1,000, okay, of whatever number you want to put in there, that's fine. But if it's not written, it's actually a base 10. And so you just have to say in your mind, or maybe just write 10 somewhere, or maybe even write 10 into the base. But you're asking yourself, 10 to the power of what gets me back to 1? And in this case, this is one of our special cases, right? anything to the power of what gets you back to 1, right? So 10 to the power of 0 gets me back to 1. And then like, let's just try like a nice pretty one just so you can see what it's like. Another nice pretty one, right? 10 to the power of what gets me back to just 10. Anything to the power of 1 gets me back to just 10. All right, the natural log is base e. You remember, e is just a number, kind of like pi, right? You can type it in your calculator and see all the decimals if you want, but we write this ln. And again, I'm not really sure why it's not an L, kind of weird. I also am not really sure why we don't just write log base e. Like, I mean, yes, it would be like 2 extra letters, and doing cursive ln is very easy, but I don't know. I don't know. So that's called a natural logarithm. And we will, let's see here. So e, we can do the same thing with these, right? They're going to be kind of similar. Nice, pretty examples. So this is like log base e. So e to the power of what gets me back to 1. And anything to the power of 0 gets me back to 1. And how about the natural log of e, right? So e to the power of what gets me back to just e? Well, anything to the power of 1. We'll work a little bit more with these. E just happens to come up like quite a bit while we're evaluating this stuff. Do an example base 10 style, right? So log of x equals 3. So now I want you to solve this for x. And I don't know, just looking at it, like, what am I talking about here? But if we think about it using the rewrite, right, we know this is base 10 because it's not written. So we're asking ourselves 10 to the power of 3 gets me back to x. And now it's like really obvious, right? Like, what is 10 cubed, right? It's just 10 times 10 times 10. So that's really easy. X equals 1,000, 3 zeros, and you're done. The reason why logarithms are so handy is because now we're going to get functions that are in the form that are in the exponential form. And so now you might be given something where you need to solve for that x that's up there in the exponent. And we don't have any other tools other than logarithms, well, and the calculator, let's face it. But how we do that is we use logarithms, and we can rewrite it, or we can bring it down and get it out of that exponent. Notice that this is different from my favorite functions, like quadratics, right? Polynomial functions before, they were in the form of where it was like, x cubed or something, or x squared, right? Where you had, this was your power that you had, and x was the base of those functions. So now we're moving away from that, and we're now making x the power, and that really makes things take off. So we need logarithms in order to solve for x. And we're going to get into more detailed examples on how we can get x solved for. For now, you're going to be getting expressions like this, where it says solve for x, and you need to do the rewrite, and then you'll be able to solve. So let's do one more example. How about something that might require a decimal? What if they say, do log of x equals -3? And they want you to solve for x again. Okay, we're going to do the rewrite. We know what base this is because it's not written. That sounds weird. We know what base because it's not written. Like, what is that? But it's not written, so it's base 10. So we're going to do the rewrite. 10 to the power of negative 3 equals what I have in there, equals x. And then now it's really easy, right? You can see this as like, oh, I know that's a decimal. Or you can see this as, I know how to deal with negative exponents. I'm going to put this over 1, and anything that's in the numerator that has a negative exponent, I put it in the denominator, make that exponent positive. And now 10 cubed has 3 zeros, 1,000. And so now 1/1000th is the same thing as 0.001. Well, let me double check. 1, 2, 3. Yeah, that's right.